And the last application in this sequence is robotics. And essentially robotics is a combination of what is called perception and action. And the perception, and we talked about this, most of the perception nowadays in robotics comes from analysis of images. So it's image processing and human text. For example, if you take a Tesla self-driving car, then most of the perception happens with video cameras. They take pictures of what happens around the Tesla car, and then the perception algorithm tries to give the description of the location of other vehicles and pedestrians and bicyclists around the Tesla car. And then the action is basically, so result of the perception is basically what's around. And then you have to take, this becomes an input to this action algorithm, and action algorithm is, can say accelerate, for example, or steer to the left. Okay, so essentially we talked about this part, the perception part, how to analyze images, and we're going to talk about more this action part of the robotics. And so a few examples in the slides, you can click and watch videos associated with those examples. But what I want to talk about, this self-driving car example. So what you see here is the images from the cameras of the self-driving car. And then the perception algorithm takes those images and basically tries to convert into this map or representation of what is around. So it has this vehicle, and it basically says, okay, there is some object here, some object here, some object here, and then also a vehicle will have a path that the vehicle wants to take. So let's say a path like this, and then there is some obstacle here. So basically, the vehicle will have to change its the current trajectory, and will take an action to steer away from this obstacle, and will have to do something like this. So a new action will be to go around the obstacle in front by steering around this obstacle. And one of the ways to learn what to do is what is called imitation learning, and it works the following way. So you basically take image from camera, and then you convert it into action. And you learn this pair from the observed actions of a human driver. So a human driver drives the car, and the cameras take the images, and then you go home and you take all of the sequence of these images, and they take all of the actions that were done by the driver, so that becomes your input-output pairs. And then you design a neural network, deep learning model, that takes the image as an input and produces action as an output. And the training data set was generated by a human driver. So this approach is called imitation learning. It is powerful, but you basically will be able to imitate this specific driver. The better approach, or more useful approach, is to use what is called reward function, and the reward function leads to another approach, which is called reinforcement learning. And reinforcement learning basically does the following. So it learns from the rewards, and rewards can be high or low. And let's say you try to learn a self-driving algorithm, and the high reward is given to an algorithm that always stays in the lane and never gets into accident. And the algorithm that gets into accident will have a low reward. And essentially try to learn an optimal control algorithm, optimal action plan, by just looking at the reward. So whenever you did something that led to low reward, you try to avoid those type of things in the next iteration of learning this control algorithm. The same approach was used by Google in the data centers. They were able to reduce the cost of the energy bills by 40% by optimally control the heating and cooling switches in the plants. And here's how this automated or reinforcement learning works. You have this what is called the Q function. Q function takes two pairs, state. So this is called state. So for self-driving car, state is basically what's around. Perception algorithm calculates the set of the objects around the car and says you have a bicycle here, another car here, and you have pedestrian approaching from the left, so that becomes the state. And then it takes an action. So it's all possible actions. And for vehicle, possible actions is to steer to the left or to the right, or to accelerate and decelerate. There's actually not that many actions a vehicle can take. And then you basically map it to what is called the Q value. And Q value tells you the value of taking this action if you are in this state. So value of taking action A when in state S. Okay, that's it. And then you design what is called the value function. Value function is basically the optimal action. So that's the so this one finds optimal action. Optimal action is the one that leads to the highest Q value. And the function V, which is called value function, basically maps the state to the value associated with the state, given that you're taking an optimal action in each of those states. And then essentially you have this simple concept and you start to do what is called reinforcement learning. In the reinforcement learning, the value function and the action function, which is called policy function. So policy function maps the state to action. You have two main functions here. And then you have a value function which maps state to its value. Value basically how good to be in this state. So if you end up to be in the accident, that's a very bad state. It will have very low value. And if you have a smooth ride on the highway without violating any of the highway rules, then it's going to be a high value state. So used to those two functions, and you use deep learning to represent those functions. And then you basically learn from observed data. So you have a self-driving car and you put it into the closed environment and you let it do whatever the car wants. And essentially put those obstacles around and you give a task to the car to go from one side of this test environment to another side of this test environment. And the car will have to learn how to go around those obstacles, and it will do it through this self-learning. It basically will understand the reward. So the only feedback that the vehicle gets from the environment is this reward, low or high, and it will calculate values and it will calculate the optimal policy as a result if you do it for many times. Same approach is used in chess nowadays. We talked about this. So it used to be this way of pruning the trees by a set of chess experts, and nowadays the trees is actually pruned using the neural networks. So this is example of a full tree, and this is play of Go rather than chess. It's actually a more complex game, and so you have all possible moves on the first move, and then moves that follow after that move, and move after that follow the second move, and you have a large tree. And essentially what neural network allows you to do, it allows you to reduce the depth with the value network. So instead of going 17 moves, you can only go 3 moves, and at the end you approximate the value of being in this state. And in the case of Go, the state is just the position of the pieces on the board, and you approximate it with value function. It's always an approximation. It's not the true value. So essentially, you don't need to build this tree with 17 layers. You can only build a tree in this case with 3 layers, so you can calculate much faster. And then you basically will choose the state. So let's say this is the state with that highest value. And then you say, okay, that's the move I'm gonna make, because that eventually leads to the state with the highest value. But also you can reduce the breadth using the policy network. You remember the policy network maps state to action. And in this case, action is which piece to move and where to move. And this policy network basically suggests you potentially good moves. And instead of exploring all possible moves from this specific state, you only explore the moves that were suggested by the policy network. And sometimes policy network can suggest you multiple states. So essentially, this reducing the width and the depth of the tree allows the search algorithm to work very quickly. And in this case, the rules are not human design, but they were learned from the previous games, from self. So you learn policy and value from self-play. So you allow one algorithm to play against the other algorithm, and then whichever side wins gets the reward, and this reward will get converted into the values of each states in between the start of the game and the end of the game. And then if you do it many times, essentially you can learn good approximations to the policy and the value functions. And in the case of the Go, this AlphaZero algorithm that does that learned in 49 hours, and it learned it good enough so it can beat the Go champion. So it took 49 hours of learning, or self-learning, to beat world champion. And if you think about this world champion in Go, it's a person who relies on thousands and thousands of previous games and hundreds years of history of the Go, and spend entire life trying to learn optimal ways of playing the game. And machine in 49 hours can outperform that human.